Hey everybody, today we will do another video, and today we will do a basic, I will say, kind of basic video on differential equations. Well, differential equation is not basic, it's not basic math. Let me rephrase it. Something basic on differential equation that will help us to solve problems. Maybe that would make more sense. But differential equation is not a basic subject. Yeah, that's... Okay, so all right, so basically what we're doing is something that help us out to solve problems, and that is called directional directional is called directional fields. Okay, so what is a directional field, right? Directional field is something that I would have it like this. Like, let's say, for example, we have an XY plan, right? So this is Y, this is X, right? And then we have a function that goes somewhere in this graph, right? So let's say, for example, you have some type of function that you don't know what it is, right? But you have some tangent line that goes to the point, right? So you have some tangent lines that go through some points. So you don't know what the function is, right? But you know that has... Okay, so you don't know what the function is, but a picture give you an idea how the function might look like. However, it might have a bunch of different solutions, but it will give you a general idea of how the function will be like, right? So let's say, for example, you have something like a point like that. Then you have another point like that, another point like that, right? Then right here you have like a point like that, and then I'm gonna a steeper point like that, and a steeper point like that, right? You know, as you can see, that this tangent point, right? This point right here, at that point, which is dy over dx with the derivative, is equal to some function of the depending on the x and y. Okay, so if that is the case, then you know that some of the general solution for this would be y is equal to, because some of this variable, somebody has to be independent variable. One has to be dependent on the other, right? And let's say that you want to make y depends on x. So then you would say that y is equal to y x. So y is going to depend on x, right? When y depends on x, you know that for any value when x is equal to something, you will get a y equal to something. Okay, so let's say, for example, that you have something like this, right? So you have something like this. You got a function that have been, um, given to us in a split in a form of dy over dx is equal to 0.2xy. As you know that this depends on two variables in this side, which is given to us as implicit. It's going to be in implicit form. This given to us in implicit form. Okay, so now we don't know how the solution will be for this, right? But what we can do, right, is assign some values. Now that we know that this is the slope, right? This guy right here is the slope. The changing y over the changing x is equal to this. So what if we assign some values of that, right? So let's say, for example, that the values are evaluated. Let's say, for example, that they are 3, 2, right? Or 2, 3. Let's see. Yeah, 2, 3. Okay, so 2, 3. Okay, so now if we come over here and we said, okay, so let's evaluate the slope at that point, right? So we say that dy, so we say that dy over dx, right? Dy over dx is equal to what? So dy over dx dy dx is equal to this guy right here multiplied by those two. So 2 times 3, right? So this times this. Remember, this is not a point, this is a comma, right? So when we calculate that, we become with a value of about 1 point something, right? So (1.2), right? So this is 1.2. So this is 1.2 is equal to the slope, right? To the derivative. So that is the slope, right? And let's say, for example, that this slope is belong to this guy right here. Okay, so let me just make this little straight lines like that, right? So let's say, for example, that this is 1.2 at that point. Okay, So we have a value given to this, right? And the value at this was 2 comma 3, and that is the slope, right? Now, if you look at this, which it's kind of hard to do it because it's not easy. I will say that this right here will, okay. So this, okay, so let's make this maybe like that, and this is steeper, right? This guy's over here less steep, and this guy's over here are steeper, right? But at the end of the day, all of them have a tension line, right? So, and this is the value for this, but then, okay, so now as you can see that if you want to connect these lines, right? So remember, there's going to be slope all over the place, right? So now look at, if you see every single place where I put a little dot in there, and I mention that the changes, the value of this change, they will land in every single one of those, right? At this point right here, so we say that x was 2 and y is 3, right? X is 2, y is 3, around that point. Is where we calculate the first value. Of course, I'm not going to be accurate because it's very hard to do this, but you get the idea that at that point, at y equal 3 and x equal 2, this is the value, right? This first, right, the first value right there. Now, if you keep doing that, changing the value of x and y, you will see that almost every tangent line that you draw over here, it will have some type of value. Over here, you get negative, right? If you put negative, of course, negative x will bring you in this quadrant. It's still y is going to be positive, but x is going to give you some type of value over here. Okay, now, if you look at, okay, so now, let's try, now that we have an idea how this will look like it, let's try to solve that differential equation, right? So we say that dy over dx is equal to 0.2xy, right? Now, if I separate the variables right here, I will say that dy is equal to 2xy dx, right? Now, this is just the first step. Now, what I need to do, I need to divide it by this guy, right? Divided by y, right? And this y cancel out. And I say that dy over y equal to 0.2x dx. Now the next step is what? The next step is somehow to find the solution, right? So dy, right? To find the solution, right? So the solution is going to be almost like the regular function before the derivative was taken plus a constant. Okay. So if with that being said, we integrate on both sides, right? When we integrate both of this, we get that this side right here, right? Take this is going to be the derivative, the integral of this is going to be the ln, right? Okay, the ln, right, of y, and then this one is going to be equal to what? It's going to be equal to the integral of this, right? So it's going to be equal to 2x squared over 2, right? So to be clear, let me use this clearly because I have a decimal, there. So what I'm doing is the following. So I'm keeping the 2 like this, right? The 0.2. I am adding 1 to this exponent and divided by the new exponent, right? Plus what? Plus a constant, plus c. Plus c. Okay, now of course, that's going to be a very small number. Okay. So, right, dividing that, and I get that ln of y, ln of y is equal to what? Equal to 0.1 x squared plus c. Okay, now let's do this. So let's bring this guy up here, right? And we have what? We have ln of y is equal to 0.1 x squared plus c, plus a constant, right? And remember that I have this ln over here. I need to get rid of that, right? So to get rid of this, I put the exponential e, right? Because this e right here with this e, this ln has a base e, right? This cancel out, right? Of course, whenever I go to the left, I gotta go to the right. I gotta do the right? Left and right the same. Dealing with equations or basic mathematics. Apply, right? So now we have an e over here. Now, if you look at this, right? If you look at this, this goes away now because, right? So because I get rid of the base of that, right? So this e cancel that. So then I get y, right, in this side. Now, if you look at this in the property of logs, that log with the same base, log base e and base e is same thing as saying like log. So e to the x plus e to the y, which is technically e to the x times e to the y, right? So the same rule applies over here, right? So now, what is the base? The base are the same. So now this guy right here is a constant. So what I can do is like, if e to the x, okay, so if e to the c is a constant, then if e to the c is a constant, right? So e to the c is equal to a constant, then this guy right here just becomes, I can say that it's a c, right? Because it's just a number. So what I will do is bring this c to here, right? And put it right there. So in front of this. So technically this is c, right? Times 1x squared, right? Now, if you look at this, right? But remember, remember, I still have, so, okay, so 1, okay, so e to the point x squared. Okay, so that is the differential equation. This is a multiplication symbol, right? I am multiplying that c, or you can actually put just a c. As long as, it's clear enough. I just want to make it clear, right? That's it right there. It belongs to this multiplying that, right? So now, multiplying that e to the exponential point x squared. Now, let's evaluate this, right? Now, let's have an idea. If this is the case, right, we have a function right now. We have a function already with a solution, right? Now, let's figure out right here. Okay, so let's say, for example, we have another directional field, maybe, right? Points like that. So now you know that this, if you want to connect these points, you see, it is going to be just keep going like this. Keep going like that, like that. You see? Now, what is the opposite, right? Now, remember that this depends on C, right? If C is greater, for values greater than C, right? Values, okay. C greater than 0 and Z is less than 0, right? If C is less than 0, then it's going to look like this. Of course, like that. It's going to be like that. So it's going to be, bottom line is it's going to be look like that. It's just an upside down curve. So it's going to be looking like this. Of course, it's not easy to do without, messing it up, because it's a lot of points that you need to connect. But the bottom line, you got an idea, right? So the whole purpose of the directional field is giving you an idea where, by having those tangential points, those tangential points, all right, it gives you an idea how the general graph would look like. Okay, so now we have an idea how it will look like, right? Based on the directional fields. Now let's do some testing, little quick. Let's do some testing just to finish this off, to make sure that we're doing the right thing. I know, because when you do this, it's better. It's instead of trying to get the right answer and trying to memorize the stuff, I think to be analytical in this problem is more helpful, right? That's what I think. Okay, so if you can see that this number right here, okay. So let's say, for example, that you want to say that x is equal to 1, x equal to 2, x equal to 3, right? The value of x. And c, just keep it, c is equal to 1. C is equal to 1. Right? Let's plot some numbers. So y equals e to the 1 times yes, times okay, square, right? Now, first value, y is equal to e point 2 times 1, right? Point times what? The first value of x, right? Point multiplied by 1, right? Square. We know that e is equal to 2.71, but because it has decimal, we need to use a little calculator. So is so 1 times 1 is square, right? So e 0.1 times 1 is square, right? So the first value for this is 1.0, right? 1.5. Next point, y equal to e to the 1 times 2 is squared, right? Then if we do that, it's going to be 1 times 2 squared. It's going to be 1.49. Y is equal to, now remember that this is a C. The C value, right? C is just 1, right? So and every single one every single value right here is multiplied by 1, right? Right? Let's multiply by 1. This is multiplied by 1, right? So now 1 multiplied by the next value is what? Next value is e to the 1, right? Times 3 squared, right? Let's see what the value for that is. So 0.1 times 3, right? So 0.1 times 3 squared, right? Now the value is increasing little by little, but it's increasing. 2.45. Isn't that what you see back here? See, that's why I'm saying analyzing this stuff is very helpful. You know that right here, when the values are increasing on the x-axis, this is increasing, right? So there was 1, and then 2, and so forth and so forth, and then 3, whatever, And you know the values are increasing if you move, go on the larger values of x, the value of y will be increasing, right? Because it's an exponential function. Okay, so, I don't have to do the rest, but if I do the negative, right? If I do the negative, it's going to be just get this value back here, right? So instead of getting this, I will be getting just the negative values, right? So basically, so when x, okay, so let's say, for example, that e, e 0.1 times a negative 1, times a negative 1 squared, right? So in this case, I'm getting the same values. But if I flip the value of c, that is when x is equal, you know, and you can analyze this, right? So in this case, right? So you got it 1, 2, 3. Okay. So it's negative, but when you square it, because you are squaring the x value, you're still getting a positive value, right? So the slope is negative, right? The slope is negative, but the value of the function, because this is the original function already that we found, right, is positive, right? Now, if I flip, if I go with the value of x is less than 0, then the value of this are going to be at c is equal, c is less than 0. The values are going to be 1 times e, right? So it's going to be 1 x squared, right? So, but it's going to be 1 squared, right? So remember that that's a 0.1. So that's going to be the same thing. So it's going to be, but c is going to be a negative 1 now. See that? It's going to be flipping the whole thing back to the other side. So okay, so never mind. So right here, hold on. So it's going to be 1, right? But it's going to be a negative, right? So, right? So when I do that, it's going to just change this value. So it's going to be negative 0.15. The next one is going to be it's going to be 2 squared, right? Which is going to be negative 1 point, actually no, whatever that number is, negative 1.49, right? All right, so it's just a mirror image, right? So now the next one is going to be negative 1 times e to the negative, not the negative, positive 1 times x. All right, so this is going to be negative 2.45. So now, if you remember from algebra, by changing the value of this coefficient, by making another copy here and making it negative c e to minus 1, right, x squared, then by doing this, right, you're changing your mirror. It's like a parabola upside down, right? So if a is negative, right, so ax, right, if a is negative, then it's going to be upside down, right? Because technically a is a coefficient of x squared, right? So this parabola, in other words, this parabola look like this. So let's say, for example, that is equal to f of x, right? Then this parabola, it look like this, or whatever. I think in this case, it just looked like this. So it looked like this, right? Same idea. But over here with the c value and the solution for differential equations. So how basically, like, how can use directional field to solve problems? Well, like I said, to give you an idea how the original problem will look like on the solution of the problem, right? By just looking at the directional fields. So that's how you do this problems. Directional fields are used in differential equations, but I mean, if you want to be like nice and neat in how to do this graphs, how to do this graph nice and neatly, use MATLAB. MATLAB will plot them very neat. Thank you for watching, and I see you in the next video.